It's the most familiar object in our sky, but it's also one of the most mysterious. Today, we're going to take a trip right to the heart of the sun, starting from its ghostly outer atmosphere and going all the way down to the nuclear furnace at its very core.
Think of this image here as our roadmap. We're going to start our descent way out in that vast, wispy atmosphere, and then we're plunging, layer by layer, into the unimaginable heat at the center. Our journey starts right now. So before we dive in, we really need to get a sense of scale. The numbers we're talking about with the sun are they're almost too big to comprehend. But a couple of quick comparisons should help us wrap our heads around its sheer size.
Okay, get this. The sun's radius is roughly 700,000 kilometers. Now that number is so huge, it's almost meaningless, right? So let's try to put it in terms we can actually imagine.
Just picture this. You're lining up Earths, one after another, right across the face of the sun. You'd need 109 of them, 109 Earths, just to get from one side to the other. I mean, that is just a truly mind-boggling scale.
And it's not just the size, it's the heat. It is immense. The surface glows at 5,800 Kelvin. And Kelvin is just a temperature scale, but to give you some perspective, a red-hot iron poker is only about 1,400 K. So yeah, the surface is scorching. But here's the crazy part. That surface? It's actually one of the coolest parts of the sun.
All right, so let's get this journey started. We're beginning in the sun's huge, and for the most part, totally invisible atmosphere. We're working our way in from the very, very edge. First stop, the corona. And that name is perfect. It's Latin for crown. It's this ghostly halo of superheated gas that gets up to millions of degrees, but it's so thin, so low density, that we can usually only see its incredible beauty during a total solar eclipse. And this crown, it's not some static thing. Oh no. It is constantly changing with the sun's activity cycle. You can see here during a quiet period, a solar minimum, you get these nice, neat streamers. But then, during a chaotic solar maximum, it just becomes this brilliant, fiery explosion in every direction. Okay, let's dive one layer deeper. Now we hit the chromosphere. It actually gets its name from its reddish color, which comes from all the hydrogen gas. And this layer is incredibly active, constantly erupting with these little hair-like jets of plasma called spicules. They can shoot up for thousands of kilometers. Okay, so we've made it through that ethereal outer atmosphere. Now we're arriving at the part of the sun that we're all familiar with, its brilliant, visible surface. This, right here, is the photosphere. And yeah, whenever you look at the sun, and please use proper protection, this is the layer you're actually seeing. It's the source of pretty much all the light and heat that makes the long journey through space to us here on Earth. But if you could look really, really close, you'd see it's not smooth at all. It's not a solid surface. It has this incredible, bubbling, granular pattern. Each of those little granules is the top of a giant convection cell. Hotter gas rises up in the bright centers, it cools, and then it sinks back down in those darker lanes. The entire surface is literally boiling. And this chaotic, boiling surface, it's also like a canvas for the sun's incredibly powerful magnetic fields. This is where we see those dark, cooler sunspots. They're just regions of intense magnetism. We also see those bright, hotter areas called plage. And then you have these amazing dark filaments, huge clouds of gas just held up in the atmosphere by magnetic arches. Okay, deep breath. We've explored the atmosphere, we've seen the surface. Now it's time to take the plunge into the truly extreme environment of the solar interior. So here's something that might mess with your head a little bit. The sun contains over 99.8% of all the mass in our entire solar system. So naturally, you'd think it has to be unbelievably dense, right? Well, believe it or not, the sun's average density is only about 1.4 times that of water. I mean, what? It's barely denser than a jug of water? How is that even possible? Well, the key word there is average. It's super misleading. This graph shows what's really going on. Down at its core, the sun is way, way denser than gold. But that density just plummets as you move outward. The outer layers are actually thinner than the air we breathe. So, okay, if the core is that dense, how does any energy get out? Well, it's a two-stage journey. First, photons of light have to basically battle their way through the super dense radiative zone. Then, in the much thinner convection zone, the energy gets carried the rest of the way by these massive boiling currents of gas.
Now, this next part is one of my favorite facts about the sun. I mean, just try to wrap your head around this. That radiative zone is so ridiculously dense that a single photon of light gets absorbed and re-emitted and bounced around so many times that its journey can take over 100,000 years. The sunlight that's hitting your face right now, it started its journey from the core before modern humans even existed.
And here we are. After all that, we have finally reached our destination, the core. This is it. This is the engine of the entire solar system. We're talking temperatures over 10 million Kelvin and just crushing pressure. This is where nuclear fusion happens, forging hydrogen into helium and releasing that colossal amount of energy that powers our star and, well, our entire world.
So this insane nuclear furnace at the heart of the sun has been chugging along, fusing hydrogen into helium for more than 4.5 billion years. Which, it leads to a pretty big question. What happens when that fuel finally starts to run out?